So the next topic that we're going to discuss here in Module 3 is all about integers. So the part of mathematics involving integers and their properties belong to the branch called number theory. Basic concepts of number theory include divisibility, modular arithmetic, prime numbers, and greatest common divisor. So where can we apply the idea of number theory? So we can apply the idea of number theory in computer arithmetic as well as in cryptology. So when we say cryptology, it is the study of secret messages. And aside from these two applications, we're also going to discuss some of the applications of modular algorithm or arithmetic to hashing functions and what we call the pseudorandom numbers. Okay? So let's just recall first about the division algorithm or the idea behind division. So when one integer is divided by a second non-zero integer, the quotient may or may not be an integer as well. So in this case, so let's just go over the different parts of the division algorithm. So we have the dividend. So this is the value that we want to partition or we want to divide. And we have the divisor. So this will be the value that we need to partition our dividend, and of course the quotient. So we can rewrite this given equation using this way. So the quotient 243 or this given dividend is also equivalent to the expression 27 multiplied to 9 plus 0. Again, 27 is the quotient, 9 is the divisor, and since we have generated a whole numbered quotient, then of course our integer is 0. So what is the significance of this given notation? So the significance of this notation is that we can derive this particular relationship wherein A is equivalent to NQ plus R, where A is equivalent to our dividend, N is our divisor, Q is our quotient. Now R is our remainder, and we have to keep in mind that our remainder is always a positive number. Okay, so our remainder can be greater than or equal to 0 and less than the divisor. So take note that the remainder is always a positive number. So there will be no case that a remainder is a negative number. So let's say, for example, we're asked to determine the quotient and remainder when 101 is divided by 9. Okay? So if we're asked to determine 101 divided by 9, then we can say that by mental calculation that our quotient is equivalent to 11 and our remainder is equivalent to 2. Okay? So if we're going to rewrite this given expression in the form of A is equal to NQ plus R. Again, A is our dividend, N is our divisor, Q is our quotient, and R is our remainder. We will have the expression, our dividend is 101, our divisor is 9, the quotient is 11, and then the remainder is 2. So as you can see here, so this given expression is valid. Okay, so 9 times 11 is 99 plus 2, that is 101. Now, what if we're asked to determine the quotient and remainder when negative 11 is divided by 3? Now, most often than not, the students will give me the quotient, let's say, which is equivalent to negative 3. And then the remainder will be equivalent to negative 2. So if we are going to follow the syntax of A is equal to NQ plus R, then we can say the dividend is equivalent to negative 11, our divisor is equivalent to 3, the quotient is equivalent to negative 3, and the remainder is equivalent to negative 2. So we have satisfied the given expression. However, if we are going to go back to the idea behind remainder, we have to take note that the remainder is always a positive number, or the remainder is always greater than or equal to 0 but less than n. So instead of having this one, the quotient as -3 and the remainder of -2, so um, we have to correct this one. So the quotient, okay, so the quotient should be equivalent to 4, and the remainder to be equivalent to, so the remainder will be, sorry, the quotient is equivalent to -4 and the remainder to be equivalent to +1. So again, if we are going to follow the relationship, A is equal to NQ plus R, our dividend is -11, our divisor is 3, our quotient is -4, and our remainder is +1. So in this case, we will have -11 to be, of course, equivalent to -11. Now, what is the difference between these two relationships, or these two values or set of values that we have obtained, is that our remainder in this case is a positive number, and now that will become valid. So there are cases wherein we're only concerned with the remainder. Okay, so I'm going to discuss with you later on the application of, or the idea behind just getting the remainder of a given problem, or what is the significance of just obtaining the remainder in a given problem. Okay, so we can present some problems in this form. Q is equal to A div n. Or in this case, we are obtaining the quotient given a dividend. We're going to divide that using our divisor. And then if we are just concerned with the remainder, okay, so this will be the operator that we are going to use. So this operator is what we call the modulo operator, because there are some situations wherein we only care about the remainder of an integer when it is divided by some specified integer. And for us to obtain that, we're going to use this modulo operator. Now, to solve for the remainder, so possible values can be narrowed down by keeping in mind that our remainder, okay, so the remainder is always greater than or equal to 0 but less than n. So meaning to say, we can narrow down the value of n. Okay, so we can specify a set for our remainder such that it can be from 0, 1, 2, 3, up to n minus 1. So these are the possible values that we can choose from whenever we try to solve for the remainder or use the modulo operator. So let's say, for example, we are tasked to determine what is 8 modulo 4. Or if we are going to interpret this given question, what will be the remainder if 8 is to be divided by 4? Again, the modulo operator will tell us what will be the remainder if a given integer is to be divided by a certain integer. So again, if we are going to apply this idea wherein the remainder is always greater than or equal to 0 but less than n, then we can narrow down the possible values of our remainder in this given example. So we know that our divisor is equivalent to 4. So meaning to say, our remainder is only limited to the values of 0, 1, 2, up to n minus 1, so up to 3. So these are the only possible values that we can work on if we try to answer 8 modulo 4. So in this case, if I am going to divide 8 by 4, we all know that it will become 2, or there will be no remainder to be generated. So in this given example, the remainder that you will obtain is 0. Now the question is, how about if you are given, okay, if you are given a problem wherein it asks you to solve -5 modulo 3. So what will be the remainder if you are going to divide -5 by 3? Okay, so I'm going to teach you a simple method for you to determine the remainder in a given using some form of a technique. So again, let's go back to the given question before. So if we're asked to solve for 8 modulo 4, so we expect the answer to be 0. Because if you're going to divide 8 by 4, you will get a whole number. So there will be no remainder to be obtained. So another way for you to, or another technique for you to solve this problem is for you to construct a clock. Okay, so you are going to construct a clock with the size given by your divisor. Okay, so you are going to construct a clock given by the size of your divisor. So your divisor is equivalent to 4. Okay, so again, your n is equivalent to 4. Now, we all know that we can narrow down the possible values of your remainder by knowing the relationship that r is always greater than 0 but less than n. So meaning to say, the possible values of remainder in this case will be 0, 1, 2, up to n minus n. So 0, 1, 2, up to 3. Now, we are going to construct a clock representing this remainder values. So this will be a clock represented by the values of 0, we have 1, we have 2, and we have 3. Okay, so again, the first step in this technique that I'm going to teach you is for you to construct a clock given by the size of n. So you have 4 values here represented by 0, 1, 2, and 3. Now, the next step that we're going to do is that we are going to start always at 0 and move around the clock using how many steps? Using our dividend. Okay, so we are going to go over this clock either clockwise or counterclockwise using the dividend that we have. So in this case, our dividend is 8. So we are going to move 8 steps from 0. Now, take note that the sign of your dividend will allow you or will determine what movement you are going to do. So if you have a positive dividend, then the movement from 0 will be clockwise. But if you have a negative dividend, the movement on your clock is counterclockwise. So let's try to do this. 8 modulo 4. So we are going to start at 0, and since we have a dividend which is 8, we're going to move 8 steps or we're going to have 8 movements from 0 and in a clockwise manner. Okay, so this is from 0 going to 1, that is 1 step. So from 1 going to 2, so that is 2 steps. Next, from 2 going to 3, that is 3 steps. From 3 going to 0, that is this is a 4th step. And then from 0 going to 5, that is the 5th step. Next, from 1 going to 2, that is the 6th step. From 2 going to 3, that is a 7th step. And then lastly, from 3 going to 0, that is the last or the 8th step. So take note that whenever or wherever we land, that is our solution to the problem. So therefore, in this case, the solution to our problem is 0. Or 8 modulo 4 will yield a remainder of 0. So let me just summarize the technique. So first, you have to create or construct your clock given the size of your n. So in this case, you are going to create a clock with a size of 4, but take note that the elements will be from 0 up to n minus 1. So that is 0, 1, 2, and 3. Next, you are going to start moving from 0 and how many steps? So that depends on your dividend. So in this case, you are going to move 8 steps away from 0. Now, how can you determine if you are going to move clockwise or counterclockwise? So it depends on the sign of your dividend. So if your dividend is positive, then you are going to move clockwise on your given clock. But if your dividend is negative, then you are going to move counterclockwise from your origin or from your 0. So wherever you land, so that is the solution to your problem. So in this case, 8 modulo 4 is equivalent to 0. So let's try to do or answer another problem. So in this case, we are asked to solve for the remainder if we are to divide negative 5 by 3. Again, we are asked to determine the remainder if we are going to divide negative 5 by 3. So the first thing that we have to do is to construct a clock given the size of our n. So in this case, our n is equivalent to 3. So our divisor is 3. So therefore, the possible values for our remainder will be from 0 up to n minus 1. So it will be from 0, 1, up to 2. So first, we're going to construct a clock with a size of 3 with this given elements. So this will be our clock. So it will be from 0, 1, and 2. Now, in this case, our dividend is negative 5. So from our origin, which is 0, instead of going clockwise, we are going to step away from 0 counterclockwise, because in this case, our dividend is a negative number. Okay? So meaning to say, we're going to start from 0 and we are going to move 5 steps away from 0 in a counterclockwise manner. Okay? So from 0 going to 2, this is 1 step. Next, from 2 going to 1, this is another step. So this is the second step. Next, 1 going to 0. This is the third step. 0 going to 2 again. This is the fourth step. And then lastly, from 2 going to 1, this is my fifth step. So meaning to say, wherever we land, which is 1, this is the remainder if we are going to divide negative 5 by 3. So let's try to prove that using the expression that we know, which is A is equal to NQ plus R. Again, we have to remember that our remainder is always a positive number, or it is always greater than or equal to 0 but less than n. So if our dividend is equivalent to negative 5 and our divisor is 3, therefore our quotient is negative 2. And our remainder should be positive 1. So negative 6 plus 1, we will have negative 5. So therefore, the remainder in this case is positive 1. So let's try to answer this problem. So what is the least possible dividend that will yield remainders 2, 1, 4 when divisors 3, 4, and 5 are used respectively? Again, we're asked to determine the least possible dividend that will yield the following remainders 2, 1, and 4 when you use the divisors 3, 4, and 5. So it's just like this way. So we are going to determine the least possible dividend, and if it were to be divided by 3, the remainder is equivalent to 2. And then next, this same dividend, if it were to be divided by 4, it will yield the remainder 1. And then lastly, A modulo, so the least possible dividend, if we're going to divide it by 5, we're going to get a remainder of 4. So how can we obtain this least possible dividend? So what we're going to do is we are going to start with the largest divisor. And in this case, the largest divisor is 5. So let us recall the relationship A is equal to NQ plus R. So we are going to determine the value of A. Our divisor is 5. Our quotient is, we still don't know yet. Okay, so and our remainder is equivalent to 4. Now what we are going to do is that we are going to sweep our quotient from 1, 2, 3, etc. until such time that we are going to arrive with the least possible dividend. And how are we going to do that? So here's how we're going to do it. So let's start with the quotient of 1. So we're not going to start with the quotient of 0. Okay? So 5 times 1 plus 4. So the least possible dividend in this case is 9. So let's try to do a reverse engineer in that form. So if 9 is the least possible dividend, 9 modulo 5 is equivalent to 4. Indeed, if you are going to divide 9 by 5, you will have a remainder of 4. But let's try to use 9 in this first relationship. Is 9 modulo 3 equivalent to 2? Is 9 divided by 3, will 9 divided by 3 yield a value of 2? Of course not. So we are going to disregard this dividend. So we are already finished with the quotient of 1. So let's proceed with the quotient of 2. Okay? So for a quotient, so let me indicate it here. So this is when the quotient is 1. So what if when the quotient is 2? So if the quotient is 2, so our least possible dividend will be equivalent to 5 times 2 plus 4. So we will have a dividend equivalent to 14. So let's try to check that one again. Is 14 divided by 5 will yield a remainder of 4? Yes. Next, is 14 divided by 3 will yield a remainder of 2? Yes, because if you're going to take a look at it, if you're going to divide 14, let's say for example, by 14 divided by 3, so that will yield a quotient of 4 and a remainder of 2. Because 4 times 3 is 12, plus 2, you'll have 14. But let's try to check that one in this relationship. Is 14 modulo 4 will yield a 1? No. So it should yield a value of 2 if your dividend is 14. So we are going to neglect this one again, and let's proceed with the next quotient to be considered, which is 3. So what if our quotient is 3? So A is equivalent to 5 times 3 plus 4. So the dividend will be equivalent to 19. So let's try to check that again. 19 modulo 5, that is 4, correct? 19 modulo 3, so there will be a discrepancy there because 19 modulo 3 should yield a 1, and then 19 modulo 4 should yield a value of 3. So again, 19 is not the least possible dividend. Next, let's proceed with Q is equal to 4. So when Q is equal to 4, so the dividend that we're going to get is 5 times 4 plus 4. So A will be equivalent to 24. So let's try to check that. 24 modulo 5 is 4. 24 modulo 3, so we will have a wrong remainder in there because 24 modulo 3 should be 0. Okay, then next, let's proceed with Q is equal to 5. So the dividend that we are going to get in here is 5 times 5 plus 4. So the dividend is equivalent to 29. By the way, this is not the least possible dividend. So let's try to check again 29. So 29 modulo 5 is 4. 29 modulo 3 is 2, because if you're going to divide 29 by 3, you're going to have 27. You should get the relationship 9 times 3 plus 2, so you have a 29. And then lastly, 29 modulo 4, it will yield a remainder of 1. So meaning to say, we can conclude that the least possible dividend is 29, given the following values. So if you are going to divide 29, by 3, by 4, and by 5, it will yield the remainders 2, 1, and 4. So the thing that you have to know in this one, or you have to understand, is if you're trying to solve for the least possible dividend, okay, so you're asked to solve for the least possible dividend, you have to start with the largest, you have to derive that from the largest divisor in the given problem. So in this case, the largest divisor is 5. And then from there, you are going to multiply, or you are going to sweep your quotient until such time that you are going to arrive with a dividend that will yield the remainder values that is required in the given problem. So the next thing that we're going to discuss are the applications of modular algorithm. So I'm going to discuss three applications of modular algorithm, and the first one is what we call the hashing functions. So the central computer, let's say for example, in an insurance company, maintains records for each of its customers. So this is the same way as our university keeping the records of the students, of the faculty, of the staff, and of the administration. So all of us are given some form of a key, let's say a student number, a faculty number, a staff number, and etc. So the question is, how can memory locations be assigned so that each customer, let's say each student, each faculty member, each staff, or each admin records can be retrieved quickly? Now, the answer to this problem, so one possible solution, actually there are many solutions to this one. So one possible solution is through the use of a hashing function. So when you say hashing function, it is defined this way. Okay, so you are given a set of keys. So this will represent a specific or unique number assigned to each person. And then each unique number is assigned to a memory location. Now, the function that maps keys to memory location is what we call the hashing function. And the hashing function is defined as h of k, which is equivalent to k modulo m. Again, the hashing function is equivalent to h of k, which is equals to k modulo m. Wherein, in this case, k represents the key which uniquely identifies each person's records, and then m represents the number of available memory locations. Now, take note that the hashing function is a type of an onto function. So, meaning to say all of the elements of the memory location is to be mapped to your keys. And multiple number of keys can refer to one memory location. So if that will happen, so there is what we call a collision. But later on, we are going to discuss some ways to resolve what we call collision in hashing functions. So again, in the hashing function, we are given a set of keys, and these keys is to be mapped to a specified memory location using this given hashing function of h of k, which is equivalent to k modulo m. So let's take a look at this given example. So let's say you are given a social security number, which is equivalent to 064212848. And take note that, let's say for example, there are 111 memory locations available. Now the question is, using the hash function, which is h of k, which is equivalent to k modulo m, how will the data be stored and retrieved in this using this given social security number? Or where is the data to be retrieved from, or where will the data be updated to if this is the social security number of a given customer? So what we're going to do is we're just going to use this hashing function. So this will represent our key or our k. So k is equivalent to 064212848. So we're going to have h of 064212848. Okay, and this is equivalent to, I'm just going to write it down here below. So 064212848 modulo m. So take note that there are 111 available memory locations. So we will have modulo 111 or 111. So in this case, h of 064212848, if we are going to apply, or if we are going to use this given expression, what is the remainder if this given number 064212848 will be divided by 111? And the answer to that is 14. So how are we going to interpret this value that we have obtained? So meaning to say, the records of the person having a social security number of 0642128848 will retrieve, will retrieve his or her record on the memory location 14. So that is how the hashing function is to be implemented. Now, how about for a person having a social security number of 107405273? Again, we're just going to apply the hashing function, which is h of k equivalent to k modulo m. Again, we have 111 memory locations available. So what we're going to do, we're just going to plug in the values in this given function. So we're going to have h of 107405273. So this is equivalent to 17405,273 modulo 111. Now, if this is the case, so what you are going to obtain as well is the memory location 14. Now, if you're going to take a look at our previous example, wherein a person has a social security number of 0642128848, the memory location his or her records can be retrieved from is at 14, memory location 14. So the same way as with a person having the social security number of 107405273. So you can retrieve his or her records as well in memory location 14. Now, what happened in there is what we call a collision. So there is a collision that happened in this given example. Now, for us to be able to counter this, what we call collision, so we are going to apply the idea of linear probing and quadratic probing. So that will be the next topic that I am going to discuss. So how can you resolve collision using linear probing and quadratic probing? So before we talk about linear probing and quadratic probing, so let us understand first again what is a collision. So by having this given example, so we have a key space here composed of elements 8, 3, 13, 6, 4, 10, and 50. Now, if we want to map this key space to here into what we call the hash table, so we're just going to map the key space with its corresponding memory location. So how are we going to do that? So obviously, the key space or the key, which is 8, will be mapped to the memory location 8. So that's how easy it is to search for a given value using the idea of hashing function, or to be specific, the idea of the hash table. So what we're going to have here is that this key, which is 8, will be mapped to the memory location, which is 8 as well. Next, for 3, so 3 will be mapped on memory location 3. Next, 13. So as you can see here, there is no memory location which is 13. So what we're going to do is that we are going to apply the hashing function, which is h of k, which is equivalent to k modulo m. Now, if you are going to take a look at this hash table, there is a total of 10 memory locations present on this table. So meaning to say, if you are going to determine where this 13 is located, so it is simply 13 modulo 10. So that will yield a value of 3 as well. So take note, this is where 8 is located, this is where 3 is located, and as you can see here, 13 is also located at memory location 3. Now, this is what we call a collision. Okay, so the same value or the same memory location is assigned to key 3 and key of 13. So there is a collision there. Next, we have 6. So 6 is mapped under memory location 6. Next, we have 4. So this is 4. By the way, this is x. Then we have 10. So 10 modulo 10. So that will be 0. So 10 will be situated on memory location 0. And lastly, the key space 50 is also situated on memory location 0. Again, there is a collision that happened in this given case. Now, how are we going to counter or resolve collision? So again, there are two possible ways to counter collision, and the first way is what we call the linear probing. So what we're going to do in linear probing is that whenever we encounter collision, we are going to move to the next available memory location. And then for quadratic probing, on the other hand, instead of just moving to the next available memory location, we are going to apply a certain relationship wherein we are going to square some form of value, and then we are going to apply that and locate that in a hash table. So that is the idea behind the quadratic probing. So I'm going to discuss with you what a linear and quadratic probing is. So the first way to resolve collision, or a simple way to resolve collision, is what we call the linear probing. Now, the idea behind linear probing is that whenever we encounter collision, we're just going to move to the next possible memory location or available memory location. So, how is that done? So again, let's start with 8. So 8 will be mapped to the memory location 8. Next, 3. We're going to map 3 on memory location 3. Next, we have 13. So what we're going to do, since the original hashing function is h of k equivalent to k modulo m, so what will happen is that we are going to modify this hashing function. Okay, so what we're going to do in modifying this hashing function is that the idea in linear probing is that we are going to move to the next available memory location. So instead of storing 13 here on 3, so we are going to store 13 on the next available memory location, which is 4. So 13 will then be stored to memory location 4. Now, how is it done? So it is done by modifying this given hashing function. So instead of using k modulo m, so the new hashing function that we are going to implement is h of k plus f of I. Okay, so h of k plus f of I, and then that's the time that we are going to take its modulo. Again, we're going to modify the hashing function such that from k modulo m, we're going to have h of k plus f of I modulo m. Take note that f of I is simply equivalent to I. So I represents another memory location, so we are just going to take one step forward. So I can be 1, 2, 3, and so on. Okay? So in here, if we are going to take a look at 13, so what we're going to have is 13, so that is h of k, so that is 13. So 13 plus f of I, so the first f of I that we are going to consider is 1. So 13 plus 1, that will be 14 modulo m. Again, we have a total of 10 memory locations. So 14 modulo 10, so that will be 4, and this is where 13 is to be stored. Next, we have 6. So for 6, so that will be 6 modulo m. So take note, we are just going to apply the linear probing whenever we have a collision. So for 6, since we don't have any collision, so we are just going to store 6 on memory location 6. Next, we have 4. So for the key space of 4, we are going to have a collision because at memory location 4, there is already the presence of 13. So what we're going to do is we are going to move to the next available memory location, which is 5. So from 4, we're going to have here, it will be stored to 5. Or if you're going to apply the new hashing function. So that will be 4 plus 1, so that is 5 modulo m. We have modulo m, so m is 10. So you are going to store 4 in this case in memory location number 5. Next, for 10, so 10 modulo 10, that will be 0. So 10 will be stored in here. And then lastly, we have 50. So as you can see here, 50 should also reside on memory location 0. But again, that is a collision. So instead of storing 50 to 0, so just move one space ahead. So 50 will be stored to memory location 1. Now, the problem with linear probing is that there is a tendency for your data or for the values to be clogged or to be concentrated in one area. Now, the problem in there is that once your key spaces or keys are clogged in or concentrated in one specified area, there is a necessity for you to apply or to modify your function all the time, because in this clogged or concentrated area, collision will always happen. So you have to modify again and again your function into this form. So what you can do is apply the idea of what we call the quadratic probing. So the next method in resolving collision in hashing function is what we call the quadratic probing. Okay, so the quadratic probing is not the same as the linear probing, or the difference between the quadratic and the linear probing is that in quadratic probing, you do not just assign the next available memory location whenever you encounter a collision. Okay, so because the tendency of that is there will be a time wherein the values will be concentrated in just one area, and we want to avoid that because in that way we will experience more collision. So in quadratic probing, so still we are going to use the function or the hashing function h of k is equal to k modulo m if there is no collision. However, if collision happens, we're going to modify this hashing function to h of k equivalent to h of k plus f of I modulo m. So as you can see here, we have retained the expression that we have used in linear probing, but this time, instead of having f of I as just equivalent to I, or the increment is just linear, which is 1. So this time we are going to have an increment, or we're going to have a quadratic increment, so in the form of I square. Take note, I is equivalent to 1, 2, 3, and so on. So whenever the necessity to avoid collision arises. So let's try this given example. Let's try to map this key space to our hash table. So for our first value, which is 8, so 8 will be stored at memory location number 8. Next, for 3, we're going to store 3 on the memory location 3. Next, we have 13. So supposedly, 13 should be stored at memory location 3 as well, because 13 modulo m, so by the way, m is equivalent to 10. So 13 modulo m, that should be 3 as well. But using quadratic probing, so we will have 13 plus f of I. So take note, we are going to start first with I, which is equivalent to 1. So 13 plus 1 squared, we're going to have 14 modulo 10. So 13 will then be stored to memory location number 4. So this is 13. Next, we have 23. So for 23, so if we're going to apply the original hashing function, we're going to have 23 modulo 10. And 23 should also be stored at memory location 3. However, 3 is already occupied, so we're not going to use 3. Next, we're going to apply the quadratic probing function. So we're going to have 23 plus f of I. Let's start with 1. So that will be 24 modulo 10. So that will yield a 4. However, the memory location 4 is already occupied. So we're going to use I is equal to 2 in this case. So we're going to have 23 plus I square. So that will be 2 square, 23 plus 2 square, we have 27 modulo 10. So meaning to say, this value or this key, which is 23, will be stored to memory location 7. So this is where 23 is situated. Next, for 43. So for 43, we're going to arrive with, excuse me, memory location 3. So 43 modulo 10, that is 3. However, 3 is already occupied. 43 plus 1 square, so that is 44. Again, memory location number 4 is already occupied. Next, 43 plus 2 square, that is 47. However, memory location 7 is already occupied. So we're going to move to the next available I, which is 3. So 43 plus 3 square, so that is 9. 43 plus 9, you will have 52. And 52 modulo 10 is 2. So meaning to say, 43 will be stored at memory location 2. Next, for 10, so 10 modulo 10, that will be 0. So as you can see here, the values are already distributed on your hash table. They do not just concentrate in one area. So that is one advantage of using the quadratic probing. And that's it for the hashing functions. Again, for the hashing function, so we are simply going to use this given hashing function k modulo m, but if there's a collision that occurs, so you can apply either linear probing or quadratic probing to be able to resolve collision. So the next application of modular algorithm is in pseudorandom numbers. So random numbers that are generated by a systematic method are called pseudorandom numbers. Because when we say random, it is perfectly at random. So there is no specific pattern in a given number. However, in pseudorandom numbers, so this kind of numbers are generated using a systematic method. That's why it is referred to as a pseudorandom. So it is pretending to be random when in fact it is not, because it is generated by a systematic way. And this systematic way is what we call a linear congruential method, or LGC. So let's try to describe what does a linear congruential method, or LGC, do. So this is the expression for the LGC, wherein x of n plus 1 is equivalent to a multiplied to xn, or the product of a and xn, plus c modulo m. So let's try to interpret, or let's try to give meaning to these variables. So when we say x of n plus 1, or x sub n plus 1, so this represents your next term in the given pseudorandom number. Again, this x of n plus 1 represents the next term in your given pseudorandom sequence. Next, we have a. So the a here represents our multiplier. So again, a represents our multiplier. So our multiplier is to be multiplied to the x of n. Now, x sub n, if this is the next term, then x sub n is what we call the present term. Okay, or this is actually the term before it transforms to the next pseudorandom number. Okay, so what is the present term, or x sub n, for the first term in a pseudorandom number? So we all know that the first term is x sub 1, and at that point n should be 0. Now when we say x sub 0, this represents the previous term, or the starting point of the sequence, and this is what we call the seed in a pseudorandom number. And then we have here c. So c represents our increment, so this is just a value to be added on this given product. And then lastly, we have m. So this m represents your modulus. So again, these are the parts of the linear congruential method, or LGC. So we have x sub n plus 1, so this is your next term. A is your multiplier. X sub n is your present term. For the first term in the pseudorandom sequence, it is to be derived from x sub 0, or the seed. Then c is the increment, m is the modulus. So we're going to have an example for the pseudorandom numbers. So let's try to generate a sequence of pseudorandom numbers using this given parameter. So again, using the linear congruential method, x sub n plus 1 is equivalent to a sub xn plus c modulo m. So these are the given parameters. So we are given a modulus of 9, a multiplier of 7, an increment of 4, and a seed of 3. So let's try to generate the first term of a pseudorandom numbers. So using x or solving for x sub 1, so x sub 1 is simply equivalent to the product of the multiplier and the seed. So that will be 7 multiply to 3 plus the increment of 4 and then a modulo of 9. So for the first term in the pseudorandom sequence, we will have 25 modulo 9, and that is equivalent to 7. Next, let's try to solve for x sub 2. So x sub 2 will be derived from, so the multiplier is 7, but in this case, instead of using the seed, which is 3, we are going to use the present term of the pseudorandom sequence, which is the 7. So 7 multiplied to 7 plus 4 modulo 9. So we will have 53 modulo 9. So meaning to say the second term in our pseudorandom sequence will be equivalent to 8. Next, we have x sub 3. So for x sub 3, we're going to have 7 multiplied to the previous term, which is 8, plus the increment of 4 modulo 9. So we will have 60 modulo 9. So the third term in our pseudorandom sequence is equivalent to 6. Next, solving for x sub 4. So x sub 4 is 7 multiplied to the previous term, which is 6, plus 4 modulo 9. So we will have 46 modulo 9, and that is 1. So as you can see here, each succeeding term in the pseudorandom sequence depends on the previous term. The first term depends on the seed, the second term depends on the first term, the third term depends on the second term, and so on. So let's try to continue solving for this pseudorandom sequence. So if we continue solving for the pseudorandom sequence using the given parameters, modulus of 9, multiplier of 7, an increment of 4, and a seed of 3, what will happen is that we are going to generate this particular sequence. So take note that the sequence is only unique for 9 terms. We have 7, 8, 6, 1, 2, 0, 4, 5, 3. And as you can see here, this 3 represents our seed. So what will happen is that if you're going to generate x of 10, you're just going to get 7 again. X of 11 will be 8, x of 12 is 6, and so on. That is why this is called a pseudo-random sequence, because it is only random for a certain amount of time, but then again, after a certain period or after a certain number of terms, it will repeat itself. Okay, so that is how you generate a pseudo-random sequence using the modular algorithm. So we are down to the last application of modular algorithm, and that is cryptology. So one of the earliest known uses of cryptology is the Caesar cipher. So this cipher sends secret messages by shifting each letter 3 letters forward in the alphabet. So meaning to say, if you have to use letter A, then this letter A is to be shifted 3 units forward. So instead of saying you have a letter A, you're going to represent that by D. So this is an example of encryption. And when we say encryption, it represents or it refers to a process of making a message a secret. Okay? So the first thing that we have to do in order to use the Caesar encryption is to express it mathematically. So what we are going to do here, as represented here, is that we are going to replace each letter of the alphabet by an integer from 0 to 25. So this is based on its position in the alphabet. So meaning to say, A will be represented by 0, B is represented by 1, and so on up to Z. So Z will be represented by 25. Now, to encrypt a message using a Caesar cipher, so what will happen is that letters are to be shifted by 3. So meaning to say, A will be represented by D, B is represented by E, Z is represented by C, and so on. Now, we have an expression or a function to designate the Caesar cipher. And this given function is in the form of f of p equals p plus 3 modulo 26. Now, we have here a modulus of 26 because we have a total of 26 letters in our alphabet. Now, this given function, we have here p. So the P represents the designated integer for a given letter. Let's say, for example, you have A. So you are going to plug in 0 here instead. And then F of P represents the encrypted value of a letter. Okay? So meaning to say, this given function maps an integer to its encrypted value. And the relationship here is F of P equals P plus 3 modulo 26. So let's try to encrypt a secret message. So let's say, for example, you don't want to be found out by anybody. So let's say you want to encrypt the message, meet you in the park. Again, let's say you don't want anybody to know that you are meeting somebody. So you want to encrypt this message using the Caesar cipher. Now, the first thing that you have to do is to represent these letters first to their equivalent integer. So M is represented by 12, E is represented by 4, T is represented by 19, Y is represented by 24, O is represented by 14, U is represented by 20, I is represented by 8, N is represented by 13, T again is represented by 19, H is represented by 7, E is represented by 4, and then for the word park, so we have P as 15, A as 0, R as 17, and K as 10. So the next step that we have to do if we want to encrypt meet you in the park using the Caesar cipher is we are going to use this given function. So for letter M, so what will happen is that this 12 represents P, or the integer or the value of a given letter in this given case. Okay, so what we're going to do is that we're going to add 12 with 3. So we're going to shift the letters forward using 3 units. So we have 15 modulo 26. So from 12, we're going to have 15. So this 15, this letter M will now be represented. So this is 15, will now be represented by P. Next, we have 4. So this 4 will become 4 plus 3 modulo 26. We have 7. This one is 7. Next, we have 19. So 19 plus 3, we have 22. So this will be represented by W. So let's map that one. So 7 is represented by H. So H, and then W, 22 is W. So meaning to say, instead of saying meet, you are going to encrypt that message using the letters P, H, W. So let's continue doing the other letters, or encrypt the other letters. So 24. So 24 plus 3 modulo 26. So that is 27 modulo 26. So meaning to say, excuse me, Y is represented by letter B. Okay, next we have 14. 14 plus 3, we have 17. 17 modulo 26. So that will be, this is 1, and then this is B. So 17 is letter R. Next we have 20. So 20 plus 3, we have 23. So that will be represented by X. So if we are going to continuously map or continuously apply this given expression, we will have we will have, for the word in, it will be represented by LQ. The word the will be represented by W, K, H, and the word park is represented by S, D, U, N. Now, instead of saying meet you in the park, so you are now you now have an encrypted message, which is PHHWBRXLQWKHSDUN. So nobody will know that you are going to meet somebody in the park. Now, the challenge here is that how will the recipient of the message react on this given message? So what will happen is that you are just going to reverse the process. So instead of adding 3, so you are going to subtract now a value of 3. So that's how you decode now the message meet you in the park. So that is the last application for the modular algorithm, and that is cryptology.